So today let's talk about references. References are a topic that is fairly advanced, but we're going to talk about this and introduce them progressively. The first thing is that we use references multiple context, and one of the common context, one of the popular context, I should say, is functions. So we have here a function, which is the main function, and let's introduce another function which will be very simple. We're just going to square the parameter. So let's call this function square, which takes an integer and returns an integer. We're going to assume for the moment that we're not handling exceptions like the number is too high and the square exceeds the capacity of I32. Just say for the moment that it's going to be okay. So the first thing you notice is that to introduce a function, I have a one parameter. I have to name the parameter and I have to give the type. Before, I could have variables are untyped. I let the compiler find out which type it was by inference when I use it. But for functions, I cannot do that. I have to specify the type by myself. And if the function returns a value, it can only return one value, and the value type is introduced like that. If it doesn't return anything, I can omit the arrow and the type altogether. So let's see how to implement this guy. So logically, it should be x times x. I say I can do that, but as a matter of time, we Rust, idiomatic Rust, prefers to use the fact that if a function last expression is the return value. So if I make an expression, right, return, I can omit the return. So the last value basically generated by executing the function square is x times x. Then that is going to be the return value of the function. Notice that I cannot do x times x semicolon because the semicolon marks the end of the expression of the statement, which means that this statement actually has no type. It doesn't return anything. And then the next one, which is this blank expression just after the semicolon, is the return value. That return value is void, is unit. So it's not I32. I have to leave it like this. And now I have a function that I can call. Let's call it this way. Let's call it as a square, and then square of, let's say 10. So that should give me 100. And 100. And if I use that with a variable, do it this way, I do this, and also I should get the same result. So let's consider what happens when I'm using this function. But obviously, if I write a function, it's because I intend to use it more than once. Otherwise, there's not much value in defining a function just for this. So if I do a second variable, call it y, let's see, y is 5, I can do that. Y, yeah. And got the result should be 125. 125. So how does this function work? We know that in the body of square, we are using the variable x, which is a parameter. But here, when I call it the first time, x is 10. The parameter value is 10. And the second time, the value is 5. So even though the name of the variable here is x, the meaning of x on the first time will be 10, and the meaning of x the second time will be 5. So there should be a way. I mean, the compiler has to make some injection, has to pass the value 10 to this function as x, and the second time has to pass the value 5 into this function. So for an integer like this, what is going to happen is the value is passed by value. So the 10 here is copied into this function, and then the next time 5 is copied into this function. And we can clearly see that this is a copy, because if we are to change the value of x, so instead of doing this, I decide to do, let's say, x, do the square plus 1, so do x, x plus 1. And I can't do that without saying that, telling the compiler that I'm changing the value of x. Like we saw before, variables are actually immutable by default. So I have to say that x is mutable, so that I can increment x. The shortest syntax for this is x plus equal 1, which is strictly equivalent to x equal x plus 1. So in this case, what I will get is 10 plus 1, 11, squared, 121, and 5 plus 1, 6, 6 squared, 36. So I should have 121 and 36. And this is what I get. But you see though that if I print the value of x after the call to the function, so now I print x, what do I get? I get 10. The value 10 hasn't changed. It has only changed, x has only changed inside the function square. So this surely indicates to me that the value 10 was made local to square by making a copy of it. And that's the principle of passing parameters by value. So now how happen if instead of having these primitive types, I use one of the compound types that we learned about earlier. So I will introduce a point, definition of a point, as two integers, x and y. So now we have point, and this function square, the square for point doesn't really make much sense, so let's call it distance. So let's call this distance square actually. And distance square is defined as x0 times x0 plus x1 times x1. And that should be that. But now it should be a point. So the point at origin. And then this point will be the point at 3, 4. That gives 25. So here we change this to, we move the mutable, we don't need that. Distance here, distance here. Right. So the only tricky thing here is that I'm trying to print the point, but I don't have a print for a point. So I only have them for primitive types. But we will learn earlier that we can derive debug and replace this with a debug break. So we can do this. What is there? Actually, this is the error comes from. Error comes from what I wanted to talk about. So let's put this print before, show that we really have 0, 0, and then print the distance. And likewise here, we can print the point y, and also then the distance. So let's give it that a shot. So we have 0.00, 0.34, and distance is 0, and distance 25. So distance here is actually square of distance. Okay, we name this as square distance. All right. So far so good. But you may have noticed that when I use this as like that, so I print it after I use square distance. And now the compiler errors. It says borrow of a moved value. So this error is something that is a bit particular to Rust. So obviously, there are other languages that have the same semantic, but Rust, I think, is the first popular language that has this semantic. So we have seen that by default, we have this value semantic, where if we have a type here, the value, when we were using an integer, was passed to this function by making a copy. But what happens with point is a bit different. Point doesn't have copy. We like everything with Rust. Rust goes for speed, performance, and they don't provide functions unless you explicitly ask for them. So we didn't ask for having a copy of a point. And if we don't, then there's no copy. Therefore, the compiler doesn't know how to pass the value x here to this function by value. So what it does instead is passing by moving the value. So moving the value means that the ownership x, the ownership of the value x, goes into this function, and then once this function owns x, owns this point, the caller cannot use it anymore. So we need to remember that when we have a statement like this, it means that somewhere in memory there's a point, and the x is now an alias for this location, for this point. Alias means that we have a name that is associated to that point, to that value. And at any time, there should only be one alias that owns that value. So here, if I just remove this one for the moment, right, because it's an error. So now we don't have an error anymore, right? It's pretty much the same as here. But if I do let z equal x, now I have z, which is an alias for the point, because z now is an alias for x, and x was an alias for point. We see that using x is no longer permitted. And the error is that the value has moved. And this is Rust's way to tell us that the alias x is no longer valid because the value has moved to z. There can only be one alias that owns the point, this value here. And this is a bit particular because we don't have that concept in most other languages. It's perfectly fine in other languages to have different variables that have the same data behind. In Java, what you would have is that x and z are two references to the same point, so two ways to access the same point. And if I change x, the value of x, for example, this coordinate, I change it. I do x or 5 was here. It's not going to be possible because x is not mutable. But let's assume for a moment that x is mutable. So if I do that, then it would also imply that z would be z.0 now should be equal to 5. I will have that. So in a language that allows me to have these multiple aliases to the same data, the confusing part is that if I change the data through one of the aliases, all the aliases are going to change at the same time. And you can imagine that the distance or the code distance between here and here could be very, very far. I mean, this line doesn't have to be next to this line. And sometimes we have action at distance because some piece of the code changing x, and then suddenly a variable that seems to have no relationship with x also changes value because they happen to be two aliases on the same piece of data. So Rust prohibits that. If you do z equal x, you have moved the data, or you have moved the ownership of x, of the point, to z, and then you cannot use x here. And this is the same thing that happens if I call this function square distance, because implicitly here, because x doesn't have a copy, and I cannot make a copy of the value, the semantic of this function call is to move the ownership of x, of the parameter, to the function, and there's no return. So once it gets to the function, I didn't give it back. I didn't say anything about returning the value. So the ownership is gone. The value is no longer accessible because x is no longer valid at the corner. So I cannot use x here. I could use x before, but once I call the function, because of this semantic here, this move, the value is no longer, the variable is no longer owner of the point, and therefore this alias, this variable, is no longer usable. I could change that by saying that I make x, my point, copyable. So again, through the derived macros, I could say it's a copy. And if I do copy, I have to do clone as well. So copy is making a copy of the value of point implicitly, and clone is making a copy of the point explicitly. So sometimes you have clone without copy, but you cannot have copy without clone. So clone would be, for example, something like z equal x of clone, right? If I don't have that, that will be an error because clone does not exist, right? And copy is stronger than clone. The same way that before we saw that EQ is stronger than partial EQ. So the difference here is that if I have copy, I don't have to explicitly say clone. I can do this. And you can see that my point here, z, is no longer taking ownership of x. It is making a copy. Therefore, I can use x. I can still use x. But if I do it this way, we have now two instances of the point, and these 2 points are different. X and z are not the same, and you can see that by changing x. If I change x coordinate to be 5, and then print x, and then print in y for z, sorry, x and z, we should see them. We should see that z is still the point at origin. Right, so x has changed to the 0.50 because of this, but z has remained the point at origin. So doing this is very different than doing what we had before, because now we have actually two different points. It's not the same as having two aliases on the same point. And having two aliases on the same point is not allowed if both of them owns the point. So, but what should I do if actually I don't want to do the clone and I don't want to do the copy? I want to avoid having to do this potentially expensive operation, right? Because when I make a copy, I'm actually allocating additional memory for that point. And you can also see that semantic is different because as having a copy, I cannot, if I touch the original value, I'm not changing the copy. So let's remove this. Let's remove this. We'll go back to what we had before. And now we want to not pass the point like by value, but we're going to pass the point by reference. So passing a point by reference means that instead of making a copy of or moving the ownership of the data through this function, I'm going to borrow for the duration of this function the ownership of the point. So borrowing is the same as in real life when you want to borrow an object. You are temporarily you're the owner, so you can do stuff, you can use it. But when the function returns, the owner still remains at x. So if we do that, we have also to say that we're taking a reference here, and now it's back to be okay, right? And I can also print the value of x afterwards. I can print it before, and I can print it after, because x remains the owner. I didn't pass ownership. I didn't move x into the function. I just borrow it for the duration of this function. So we can call this, and we have, oh, okay, so we borrow here, and we have to borrow here. Right, so this is exactly what we expect, right? 0.0, 0.0 could print x before and after, and then we could calculate the distance. So this little notation, this ampersand here, means the reference, that we are passing a reference. So again, the reference is saying that point doesn't move, but we are giving to square distance the location in memory where point is. And so that allows this function to use the point, because now it knows where the point is, but it will not take ownership of that point. So this is one usage of a reference. Another usage of a reference is called a slice, and they're related to our previous topic, the vectors and arrays. So if you have a vector or an array, let's go with a vector. They are used actually more often than arrays. If I say that we have a vector of 100 integers, right? And I want to pass that vector to a function. So let's say function f, and I want to pass the vector. The same thing could happen here. Pass it as a value to i32, and then I can do stuff with a. And I can do stuff with x inside. This works. But again, the same way as happened before, by doing this, I pass the ownership of this variable to the function f, and afterwards, I am not allowed to use it. So if I do just print of a0, you see that a is also borrow of moved value. Forget about this borrow here. The important thing is the moved value. And this is the same reason, except that instead of having a point as before, I'm actually talking about a vector. The vector and point are both complex objects that do not compound objects that do not have a copy operator by default. They cannot be copied by default. So to fix this issue, what I would like to do is to pass the vector by reference. So that's easy. And in the case of a vector, what I can pass is a slice. So a slice is written like this. The braces operator that looks like an array, and again this ampersand that indicates it's a reference. So this notation is a slice, and the slice in this context is more than just a reference to the beginning of the array, because the array has more than one element. Before, for a point, I could have only one point, and therefore the reference was the reference to that point. Here I'm referring to a slice of an array. So what I'm going to get is the reference to the beginning of my slice, but also to the length of the slice. And the slice doesn't have to be starting from the beginning. So what I'm going to print here is both the, let's say, two things. Let's say I want to print the first element of my slice, and I also want to print the length of my slice. So these are the two things that could be useful. And here I want to make these elements different. So I'm going to make them like 1, 2, 3, 4, 5, 6, 8, 9, 10. Again, this is really not the best way to initialize a vector like that, but that would do for the moment. And now the last error is, you can see first that this is no longer an error, because I'm not passing the vector by not moving the vector into the function f. I just borrowed it for the duration of f. But the thing here, as before, we need spatial syntax to pass a slice. And in this case, we have an operator. We can pass it like that. Right. This is the slice that is the entire vector. So if I do this, I expect to see a to 0 to be 1 and the length to be 10. So let's give it a shot. Right. So you see 1 and 10, and it prints a0, which is 1. So now if we take a different slice, with slice from the middle, I could pass from, let's say, 3 to 5. So 3 to 5, the index starts at 0, So that would be element 4, 0, 1, 2, 3. And the slice does not include the last element. So 3 to 5 is actually only element 3, element 4. So we should see here a printout of 4 and 2. So let's run this. And we got 4 and 2. So this is a slice. The slice which has a similar syntax as a reference, as a borrow. But we see that for a vector, a slice is more than just a reference to an element. It has also the length. So that's it for today. Next time we'll look at a particular type of slice, which are the string slices. And all this stuff will actually be needed when we talk about strings.